Good afternoon. Quick question to start us off. Anyone here involved in a day-to-day calibration activities? A small number. Anyone produce anything that needs to be calibrated? It's going to be most of you. Okay, great. So this talk is going to be focusing on engine calibration activities, and you're going to be seeing one of our products called the Model-Based Calibration Toolbox. We've got 90 products. Chances are there's some of them that you are not so familiar with, so it will be a good chance to see what that can do. Okay, somebody stole my slide from yesterday, so you've already seen this. What I wanted to do is just talk about a couple of the challenges in calibration right now. What are people working on, and what's the how to check as you're gathering data, how to check that that data is good, how to check that it's going to support your calibration activity, that a wire hasn't fallen off or something hasn't gone wrong with your engine. Okay, and the third one is probably the most interesting. I think I'll spend the most time on that. Data quantity checking. It's simply saying, when I'm doing my calibration, how do I know that I've got enough data to do a good quality calibration? Okay, how do I know I've got enough data that will be accurate enough, that I will meet my emissions targets, and that I will meet my performance targets? Okay, so let's jump in. I think that some of you aren't familiar with what model-based calibration means. So I'll just spend a moment or two talking about that. It's really this five-step process. No one can see that, right? Okay, so it's this five-step process to get from an engine with no calibration to a good calibration on the ECU. So step one, design of experiments, talks about how we're going to plan the tests that we're going to run on the dynamometer. Okay, and some of you will have used DOE for engine applications. Some of you may have used DOE for completely different applications. Okay, you then go and collect the data, and the third step is the modeling step. Okay, we've talked about two kinds of modeling in this conference so far. One of them has been the controller modeling. Okay, putting your Simulink stateflow blocks of how the software will behave. We've talked a bit about plant modeling. It's using our textbooks, laws of physics and so on, to capture how a system behaves. This is a third kind of modeling here. This is statistical modeling. Okay, this is taking data and identifying underlying behavior from that data rather than from physical laws. Yeah, have any of you done statistical modeling? Well, have any of you ever fitted a straight line to some data? That's statistical modeling. What we have here in our model-based calibration toolbox is a much fancier version of that. Okay, many variables, many different model types to accurately capture these high-dimensional behaviors. Okay, so every time I'm talking about modeling in this next 20 minutes, I'm talking about taking data and identifying effectively surfaces to capture the responses I'm interested in. Might be torque, might be temperature, might be certain emissions levels and so on, as a function of the inputs, whether they be from the driver, speed, load, or whether they be from some actuators, cams, EGR, and so on. Okay? The models are then used for model-based calibration by applying an optimizer to them. Okay? So we'll set some objectives, some constraints, and find some best lookup table values for that. And finally, they're put onto the ECU. I'll spend about 2 minutes now just showing you what that looks like. Okay, so this is Model-Based Calibration Toolbox. I have just wanted to show you a couple of the couple of the features. I brought in some data. There's my data, imported via Matlab, of course. Okay, and lots of ways to view that, filter it, and so on. Okay, what if I wanted to do some DOE? Yeah, so we've got a nice tool for that. Okay, so I'm going to create a space filling design with 100 points, let's say. Yep, using this Halton sequence space filling design type. There it is. I might have some constraints on the space. I might have some existing data that I'm building that design around. Lots of possibilities, but pretty easy to do. Let me show you the modeling part. This is where I take the data and I've built some surfaces. The process usually is that I'm going to try out some different model types. Choose one that seems to fit the data well. I might be changing the number of parameters of those models or other settings. Okay. So what I come up with, I'm looking here at a torque model. I can only show 2 variables at a time on my screen. Okay, so this will view in terms of speed and load. You'll see the coloring here. The area outside is outside the boundary of the data. Yep, so when you're interpreting these fits, you want to know where was the data. Does the behavior look correct? Lots of other views that I might be interested in. I might want to view sort of predicted against actual for this model. There it is. I can look at all kind of different trends, one variable at a time. Okay, move things around. All built in Matlab. Very large Matlab application, basically. Okay, so that's the modeling part. I should also point out that you can do all this stuff from the command line. Lots of tools for automating that process. Let me just bump up the font for you so you can see what's going on. So I've created this project object. I might look at the data in there. Okay, there it is. Lots of properties, lots of functions I can call on that. There they all are. Okay, I can do all that by the command line. So usual process is you would explore how to do the